Hello, everybody, and good evening. Welcome back to Ask Math Anything. We haven't done this for a while because I've been doing a lot of collaborations with various math competitions. But a tradition we started really about a year ago was that we started running a session where every week, actually it was every day almost, I would go and answer questions that people randomly ask about math. Now, in order to make this thing as widely accessible as possible, we chose to talk about topics that might be around algebra or geometry level, but sometimes those questions might be quite complicated. I mean, they would be algebra or geometry, but they would often be math competition type questions. So we're going to continue with that. And the way this always works is that people are able to ask questions as they go, and then we can answer as we go too. I just saw somebody give me some feedback that the camera is out of focus. Is that the case? Actually, I'll say that. I think that my hair is out of focus. I mean, my hair is really messy. But actually, I think that it might be that YouTube is a little bit blurry sometimes. But as far as I understand, our camera is good. Okay. Well, what kind of questions do we have today? I see that. I mean, I'm just going to answer like random questions that come. Okay. I see one that's interesting. Snake Queen, can you explain converting between bases? Yes. All your base belong to us. Actually, I'm not sure if that reference works with this audience, but let me go and adjust my system very slightly to be able to answer your question about bases. Okay, so how do you explain converting between bases? Well, I'm actually going to talk about the interesting kind of converting between bases, because there's the uninteresting kind of converting between bases, which is called convert it into a normal number. Oh yeah, what's a base anyway? If I wrote a number like, I don't know, 75 in base 9, what does that mean? That means that, let's have a bigger number, okay? Like 275 in base 9. What this means is that this is worth 1, this is worth 9, and this is worth 9 squared, which is 81. That's how bases work. It's like in base 10, this is worth 1, this is worth 10, this is worth 10 squared. And so what would this be? You could convert this into base 10. And if I wanted to convert this into base 10, I would say it's just, let me write it the other way. It's 2 81s plus 7 9s plus 1 5. Actually, in order to be more systematic, I'll say plus 5 1s. Okay? And you could just turn that into a base 10 number. And if I wanted to turn this into like a base 8 number, I would just kind of undo that process. Now, a lot of people will learn that in school. What I want to show you is a nifty thing. What if I wanted to convert this into base 3? Well, what would it mean if I want the whole thing in base 3? I want to know what it is in base 3. In base 3. Well, now, I would need to go and figure out how many of each thing I want, right? Because in base 3, well, this is worth 1, this is worth 3, this is worth 9, this is worth 27, this is worth 81, and this is worth 243. So if I wanted to convert this into base 3, I would need to go and figure out how many 243s are there. But I'm lazy. Anyone who has watched my live streams know that I'm just a really lazy person. And doing this kind of calculation, no fun. It's going to take me too long. So here, let me show you a neat trick. Oh, there are 281s, right? Hey, let's try this. Let's put 281s. I don't see any 243s. Let's put 0 there. And I've just taken care of the 2 times 81. Well, let's see. I have 7 9s, right? So I know what I should do. Let's do the same thing. Let's put 7 there. What's wrong with this? Why is this a really, really terrible thing to do in base 3? I would like my number in base 3 to be 0 to something and then 7 and something and something. What's bad about this in base 3? Well, the problem is that if you write a number in a base, your biggest digit is that base itself. Like that's actually what a base arithmetic is. Yes, indeed, I am cheese says it is over 2. So the issue is in base 10, I could have numbers that go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the whole point of base 10 is don't put a 10 there. Use the place value. Put the 1 in the next spot and put a 0 there. There is no 7 in base 3. So what do? Oh no, I don't like 7. But you know what? What if I convert 7 into base 3? You know what 7 is? 7 itself in base 3, that's like 2 3s plus 1 1. Because 7 in base 3 is 2, 1 base 3. Is that okay? Like if I want to convert 7 to base 3, it's like 2 3s and a 1. Yeah. But you know what? Let's now multiply it by 9. This thing times 9. Look how this works. This will give me 2 times 3 times 9, which is 27, plus 1 times 9. See how that worked? I just did a kind of a distributive property where I put the 9 into the 3 and I put the 9 into that 1. Ooh. Now I have a better idea. Let's not put a 7 on the 9. No, no, no. I see that I can do this with 2 27s and 1 9. 2 and 1. That was cool. I can do that again. You see, if I want to do the 5 1s, I can't just put a 5 there. I cannot put a 5 there because 5 is not a digit in base 3. But what I could do with the 5 instead is I could take the 5 and convert the 5 into base 3. That is 1 3 and 2 1s. Because 5 in base 3 is 1 2 in base 3. And if I want that times a 1, well, that's just equal to 1 times 3 plus 2 times 1. So I could put a 1 and a 2. And what I just showed here is if I'm converting number from a base of 9 into a base of 3, because 9 happens to be a power of 3, all I have to do is convert each of those base 9 digits into base 3 and just like write them down and slap them together. And that's it. So this is cool. This is a cool trick. And there's a lot more about converting to bases, but let's use that as the answer to this first question that was asked. What other questions do we have? Let's see. What other questions do we have today? Oh, neat. Some person has asked, what is the proof for same length tangents? I think I know what you're talking about. What you're saying is, suppose I have a circle. Here's a circle. Looks sort of like a circle. And if I draw tangents, that means that I've got some point here. And I want to draw the tangents to that point. That's like this. That looks pretty tangent. How do I do another one? Sort of tangent, okay. And look at that. The lengths are the same. Length is that, the distance from here to there is the same as the distance from there. It looks pretty close. Okay, that's nice. And now the question is, how do I know they're the same length? It's like, why are they the same? Why the same length? One of the most important parts of math is symmetry. Just noticing that if you flip something over one line, it's like the same picture as it was before. And the same tangent lengths have to do with that symmetry. And that's because circles are really symmetric. Here's how I'll talk about it. So the circle has a center, right? Here's the center of the circle. And right now, I don't yet know that they're the same length. You asked me to prove why they're the same length, okay? So I don't yet know they're the same length. But I think that there's going to be an interesting line of symmetry here, which is what happens if I were to just draw a line right through the center and through that point. That looks like a nice line of symmetry. Well, how can I prove anything about that? The one thing that we know about tangents is that if you have a tangent to a circle, then if I draw the line from the radius, if I draw the line from the center to that tangent, that makes a 90-degree angle. Okay, so I know this so much. I know this so far. I know that these two are 90-degree angles. I also know that these two are the same length. Actually, they're both radii, so of course they're the same length. And now the situation here is I have right triangles. Oh, they're the same hypotenuse. Look at that. That's the same hypotenuse. So they have the same hypotenuse, and they both have this same length r, and they're all right triangles. Hey, can anyone tell me why these two have to be the same length? There's a really good reason now. The really good reason is that these are both right triangles. They're congruent triangles. Yes, they are. And how do I know that they're congruent? Like, what would I use to conclude that they're congruent right triangles? By HL, says Leo Yang. Yes, by HL. SAS proof. You see, this is where I'm asking. What is SAS here? Do I have SAS? What is the SAS? SAS means that it's like side and then an angle in between and then a side. But if you look at what I've drawn here, that's a side, That's a side, but the angle's over there. That's not SAS. That's SSA, right? I have like side, side, and angle. It is not actually necessarily true that SSA gives you congruence. So in that case, what do I do? I have to be more careful. You called it HL, but there's another way I can call it. It's like, if I have a hypotenuse of a right triangle and I have a side, do you know how you could figure out the other side? You could use Pythagorean theorem. It says, I am cheese. Yes, you can use Pythagorean theorem. Oh, don't say you're a noob. It's okay. I was just trying to point out here that I actually was like, oh yeah, let's just use SAS. And then I was like, not exactly SAS here, but because of the Pythagorean theorem, I would be able to know that the length of this side is the same calculation you do as the length of that side, because they both use the same hypotenuse, and they both use the same that side. So you can actually use this a squared plus b squared equals c squared thing. And the length, we even know what's the length. The length is, oh, why did I call it hypotenuse? Well, I did. Hypotenuse squared minus the radius squared. That's that length. So this is just going to work, and that will tell you that these two are both the same length. And some people call that HL congruence, hypotenuse leg. Okay, neat. More questions. What other questions do we have from today? Astro B7. Prove the Riemann hypothesis, please. That's kind of hard. I don't know anyone who knows how to do that yet. So I think you'll have to ask a different person on the Ask Person Anything live stream. More questions. How wide is a triangle from area? I don't know. Let's find out. So that's an interesting question. How wide is a triangle from area? Okay, I like this question. Because at first you'd be like, oh, well, if I know the area, then it maybe can't be that wide, right? Like, suppose I tell you the area is so small. So, suppose I have, how about if the area is just like 1 square centimeter? Like, that's tiny, okay? 1 square centimeter, that's tiny. Does that mean that the triangle better not be very wide then, right? It's like, come on, if I've got 1 square centimeter, you can't have that wide of a triangle, can you? Oh, but you can. There's like some really interesting triangles out there. And you know what? I don't want to do one. Half, half, half. Half is going to be fun because we're going to do something quite interesting. Half a square centimeter, okay? So if I have half a square centimeter, how wide could that triangle be? Well, it turns out that you could make it pretty small, okay? You could do this. 1, 1, and this. And that's like that's not very wide. That's like only 1 wide. Is that it? But Liu Yang's right. As wide as you want. Not quite infinity, because then it wouldn't be a triangle. To make a triangle, you need to have 3 points that are connected together. And if I'm infinity, it's like, where are the points? You know what I mean? I'm trying to say if you went really legitimately infinity, you don't even have 3 points. So the situation here is it turns out you can make it as wide as you want, which is better than saying infinity. Those are different things. The correct answer is arbitrarily large. But not infinitely large. Okay? These two are different concepts. To say arbitrarily large, that means that, well, it could be as large as you want. To say infinite, it's like, it's really infinite. And to give you an example of the difference, it's like, well, there are arbitrarily large real numbers. You know what I mean? Yeah. Oh, there are prime numbers that are arbitrarily large. That's true. There's a proof of that. You can get like as big a prime number as you want. But it is not true that there are prime numbers that are infinitely large. Like, what is that anyway? Like, is infinity a prime or not? I mean, no, it looks like a sideways 8, and 8's not prime. No, don't listen to that. That's bogus. That's not the way to think about whether infinity is prime or not. But the point is, like, arbitrarily large and infinitely large are different notions. And now the infinitely large, it won't be infinitely large, because if I've got a legitimate triangle, I've got 3 legitimate points, and there's like a legitimate distance between them. It's not infinite. Okay? So now the issue is, how can I make it arbitrarily large? That's actually cool. The reason I showed you this 1/2 is there's a neat fact. And some of you will learn it at some point, especially if you play with a lot of math competitions. But imagine I have a grid. Okay, so here I am making a grid, and I've made the mistake of making a fairly big grid. So now we're going to take a while as we draw some dots. We can sing a song as you go if you want, but you know, dum de dum. Here we go. We're making this grid of dots. I somehow decided I wanted a square grid of dots, so here we are. I think we have successfully finally made a grid of dots, and it's sort of like a grid. So what I'm going to do is I'm going to start connecting some lines, connecting some points, some dots in this grid, and I'm going to try to draw straight lines. Oh my gosh. Okay, I drew a straight line, tried to at least, and I guess I can draw another straight line. Let's go here, and let's go here. That is a triangle, okay? That goes through 3 points. This point, and this point. Does anyone know what's the area of this triangle? The area of this triangle is pretty cool. So let's go and work it out first, where we just kind of work it out by, well, how would you figure this out? Suppose somebody gave you the problem of like, what's the area of this triangle? How would you solve it? Some person thinks the answer is half, but why? Why? How would you go about trying to solve for the area of this triangle? Well, sometimes the way you do it is you just use half base times height, right? Oh, but that's no fun. What's the base? I could use the Pythagorean theorem for that. What's the height? Ew, that'd be bad. But what you could do here, and you're right, people are telling me you could make like really long skinny triangles. That's really what I'm doing here. But I'm trying to show you a really, really neat fact, which is like if I draw this like bunch of grid points, and then I somehow draw this. Yes, thank you very much. Po-Shen says, okay, actually I was going to go for Jiang Michael's rectangle minus triangles. Let's start with that first, okay? And I also saw that Po-Shen says Pick's theorem, and Eric Huang says Pick's theorem, and that's actually what we'll go to soon. But the first thing we'll talk about is like, let's just subtract stuff, right? What if I just went and took this rectangle and subtract out some triangles? Totally legit. So what's the area of the rectangle? This is the hard part. What's this? 1, 2, 3, 4. It looks like it's 4 by something. So it's 4 by 1. I'm counting gaps. 1, 2, 3, 4, 5. 4 by 5. Okay. So that means that the rectangle is 4 times 5, which is 20. Okay. So the rectangle is 20. But then subtract triangles. Nice idea, right? So I want to now subtract some triangles. Well, I've got this top part, which is half base times height I can do for that, which is half of the 4 times 5. That's 10. But then I have to subtract some more stuff, right? So I also have to subtract off, oh boy, let's go and make some stuff. I'm going to have to cut this a few more times. Are people okay with what I just chose to do here? I'm going to say there's a triangle there, and then there's a rectangle there. So if I'm going to subtract those off, well, this one over here, this is going to be only 4 across, and it's only 3 up and down. Okay, so that's half of 4 times 3, which is 2 times 3, which is 6. I also have to subtract off this rectangle thing. That's a 3 by 1. So that's a 3. And I also have to subtract off one of these other things. And that thing is like a 1 across, 1 up and down. So it's 1 by 1 over 2. Okay, that was supposed to say half. That says half inside there, okay? And what happens if you subtract? Oh, look at that. It's 20 minus 10, which is 10. And then minus like, that's 9. Like minus 9.5, right? This whole thing I'm subtracting is 19.5. The answer is half. That's neat. So actually what I did is I just kind of drew a triangle where all 3 of the points happen to be points of the grid, and there's no other points on any of the sides of the triangle, and there's no points inside. And there's a really neat fact, which is called Pick's theorem. And Pick's theorem tells you that you should not pick your nose. Well, actually, no. Pick's theorem tells you that if you have any triangle where all the points are on the grid, and there's no other grid points on the sides, and also no grid points inside, then the area of the triangle is just exactly 1/2. Well, there's actually a more general way to write Pick's theorem, which I even forgot. What is it? So let's see. What is Pick's theorem? Pick's theorem, which is that if all of the vertices, so if all, yeah, they're called vertices, all of the corners, all of the vertices of a triangle are on the lattice. Well, they're actually called lattice points, but I'll just call it grid points, okay? Grid points, the area equals, okay, what is it? There's some formula here. And it actually turns out to have a combination of the number of points on the interior and the number of points in the boundary. I seem to remember it's interior plus half of the boundary. And it might be plus one or like plus half, plus one, minus one. We'll figure it out shortly. But the way that this makes sense, by the way, so far this part makes sense because points on the boundary should only count like half if you were ever going to prove this by a method called induction. But what you have, oh no, is there a problem? Is 5 by 6 not 4 by 6? I think we're okay. I was counting the number of gaps, okay? But this is not right. We need to subtract some stuff here. So the reason, by the way, I'm going to write a minus sign just so that no one thinks that I was claiming that was the answer, right? But the point is that it makes sense to count one for each, like one area unit for each one of the dots inside. Because if you drew like a ginormous triangle, well, you know, like each of those things inside is sort of like at the middle of its own 1 by 1 unit square. So that's why you should not have a half on the I. And the B should have a half because of the fact that if something's on the boundary, it could count towards each of the, like if you were to draw another one on the other side, like another triangle or another image on the other side. On the other hand, here I need to put some minus sign. So if you look at what we've got here, by the way, the number of interior points is 0. The number of boundary points is 3, right? The number of boundary points is 3, 1, 2, and 3. That includes these vertices. And so it's going to be 3 halves, and I need to minus a 1. Because the answer was 1/2. So I think this is Pick's theorem. And actually, you guys have access to Wikipedia and all these things, which I don't. But I think that's actually going to be good for Pick's theorem. But the neat thing is if you ever draw something for which there's no interior points and all 3 of your corners are on the grid, then actually the area is always 1/2, which is really neat. I just thought it was really neat that if you draw any grid triangle you want that just happens to have nothing inside and just has each of the corners on these grid points, boom, the area is going to be half, which is nice. Okay, more questions. What else do we have? Ooh, somebody asked, can you explain the inclusion-exclusion principle? Yes, I can. But to save you the time, not to save you the time, to save everyone the time, that's already on YouTube. I actually put my entire Carnegie Mellon University combinatorics class on YouTube. And we talked about the inclusion-exclusion principle, I think in the second-ish or third-ish week. So if you just go to my YouTube channel and look for Carnegie Mellon University combinatorics class, discrete mathematics class, you'll find it. And then you can see an explanation there. Okay, more questions. Wow, now we got lots and lots of questions that came here. Oh, interesting. Somebody asked, Anitue asked, how do you use infinity in real life? So I think I personally don't use infinity that often in real life because I don't find that many things in the real world are actually infinite. You know, like it's not really that I'll go an infinite distance anytime soon, and I can't go an infinite speed either. On the other hand, I often think about the notion of going towards infinity. So for example, maybe if I'm thinking about, yeah, here's an example. I'm working on some app right now, which is trying to stop the spread of disease. And oftentimes we need to think, what happens if we have more and more people using the app? How much computation do we need to do? Are our computers fast enough? So we think about what happens as the number of people using the app grows towards infinity. Of course, there aren't infinitely many people in the world. However, it's still useful to be able to say, as I'm having more and more people, if I double the number of people, how much more computation time do I need? And if you think about things being very large, like converging towards infinity, then oftentimes things become like, well, if I double the number of people, I take approximately double the amount of computation time with that double number of people. And the key word was the approximately, because it's not like exactly double the amount of computation time. There's always like a little bit of stuff on the edges that changes. But when you think about things being big enough, it's convenient just to be like, well, it's approximately double. And so I guess I often think of infinity as, I think of the notion of infinity as if the things I'm computing get bigger and bigger, then what happens? Okay, more questions. Oh, interesting. So, Jiang Michael said the zero is the opposite of infinity. So, in some sense, if you're thinking about zero, maybe you're sort of thinking about infinity, but the opposite. That's neat. More questions. Oh, Bob Smith has asked intuition behind Pick's. Yeah, so the idea is if you actually want to prove Pick's theorem, you can prove it by something called induction. But the intuition behind Pick's theorem is also related to this notion of things getting very big, like infinity. It's like if I got a giant rectangle, the interior points should each count as like one full score in terms of like 1 unit of area. Because as your rectangle gets bigger and bigger, the fraction of the points that are interior points becomes close to 1. It's close to 100%, almost 100% of your points are the interior points. And by the way, each of the interior points, you could imagine, has like a 1 by 1 square centered around it. And at that point, it really does make sense. It's like each of those ones counts me a square of area, right? Like if I actually had around each of those interior points, if I said that's a square, that's a square. So the intuition behind Pick's theorem is that somehow, yeah, it makes sense that the interior points give you one score. Because if I imagine putting them out, I do see like all of them lining up like this. So that's one of the intuitions. And the boundary points give you like half score. Because if you think about what's going on the boundary, it's like this. It's giving you like half. Of course, that's what's going on when you have something which is perfectly rectangular. But the general intuition is that's why that would be a half score, because the boundary is like if you put unit squares centered around those grid points, that's only half of it. Okay. Of course, the best way to prove this is by a proper induction, but you asked for an intuition, so I hope this is useful. What else? So Leo Young has a general question that's about learning, which is, how would you recommend transitioning from answer-based math to proof-based math, like the jump from AIME to USA JMO? So this is very specifically talking about the kinds of mathematics that you see in math competitions, especially when you transition into the high school ones, where you have to explain things. So my angle on this is, I think it's really healthy, even when you do the answer-based math, to always think about the why. Which is why, like, when you ask me random questions, I always try to give you explanations with a why. And ideally, I try to show you things which have multiple different ways to see the same answer. The easiest way to transition to proof-based math is to always be thinking about multiple ways to see the same answer. And to also think about why everything is the way that it is. And if you are used to that, then it's easier to transition to those proofs because you've already been thinking about explaining why things are. Now, if you're actually trying to learn the skill of how to come up with a proof, yes, that one does actually take some very focused work on questions where you have to think of like why something is true and explaining a proof. On that one, I recommend there's a lot of, actually, I think they're free contests. Like there's something called the USA Math Talent Search, USA MTS. They'll grade it for you. And I think it's free. And so you should just play in these kinds of contests where you can try to write a proof and you can try to get some feedback on how convincing were you and explaining that something is true. Another way to get used to proving things is to try to explain to other people around you why things are true. Like if you help people with their homework, or if you're in your math class, you help the people sitting around you, the goal should not be, hey, just like do it this way. Instead, try to explain why the things are true. Okay, more questions. What's the wideness of a green shirt? Depends on the shirt, I think. Depends on who's wearing the shirt. Although actually you shouldn't, well, I guess you could. I was going to say a shirt is three-dimensional, but you can also quantify the concept of a width as well. Okay, more questions. Okay, Soidul Enjoy says, what is the concept of alpha lambda definition? I actually don't know what you're referring to. And I don't know the answer to everything by any means, but if you could be a bit more specific, that might be helpful. I actually have not heard about that before. More questions. Oh, interesting. Rhodion RR. How can we find the area between two circles that they are not one inside another? So if I want to draw two circles, Oh yeah, okay, okay, I can see that. So I think I know what you mean. Yeah, I think you mean the common area. If I had one circle and another circle, and I want to know something about the area that's between those two circles like that, I think what you might mean is inside both of them. The way that you do this is you actually can, you always have to cut your picture into things that you can calculate areas for. For me, circles always have centers, so I draw the centers first. And a nice thing that happens is that if you look at this line that cuts, now I actually can say I have two sub-problems to solve. And each of the sub-problems has the same style. See, if I draw this triangle here, I could try to figure out this area. And if I can figure that out, then I can do the same from the other side, right? So the point is, I just want to be able to break down this area in between into something that I could conceivably calculate. And I can definitely calculate it as this yellow piece plus the other one. So if I just know how to do that, I'm good. But this one I do know how to do, because I can figure out this one by saying I have a fraction of a whole circle. Think of it as a fraction of the circle, like this, for which I just need to know what angle I have there. So I can figure out the fraction of the circle minus the area of that triangle, and I'm good. So I'm just going to say you can do it all by just knowing that particular angle. And if we wanted to know some things about the angles, oftentimes we will write the angle like by a theta or something. And so if I had the radius of the circle being an r, right, here's an r, here's another r, well then I can write that this piece, that's just the area of that, that's equal to pi r squared times the ratio of the angle that it is. Let's use degrees, okay? Theta over 360 degrees times pi r squared, that's that piece. And if you want to subtract out the area of that triangle, I will say usually I don't use trigonometry in this live stream, but because the question that you asked might, I don't know what is the background of people who are here, but if I happen to just have the radius and I just have that, that particular angle, it's actually quite nice. You can use trigonometry to say that the area of this triangle that you want to subtract off, that was not isosceles enough. The area of this triangle that I'm trying to subtract off, not sure that's much more isosceles at all. And actually I want to emphasize it's not equilateral. So let's do this. It's because it's running into my head. And because I'm not wearing a green shirt, I have to be careful about my space. But so that's the theta, theta, and the r. And the area of that turns out to be 1/2 r squared times the sine of theta. And if you're curious why that's true, the reason that's true is because you can always draw a perpendicular here. And what trigonometry then tells you is that the height of this thing, because there's a right triangle where r is the hypotenuse, and this is a theta, then this length here is r sine theta. So actually this 1/2 r squared sine theta is just coming from the half base times height. Anyway, so this is a way that I would be able to find out the area between the two circles. I would just do it on this and do it on the other. And the question is, of course, when you look at a particular problem, what information is given to you? Sometimes you have enough information to do it just like this. Sometimes you need to find this information or find some other similar information to let you do the same thing. Okay, what else do we have? Wow, people are talking about quantum computing. This is getting pretty sophisticated. What else do we have? Nobody asks, what is the squirt of 4761? I don't know, let's find out. Square root of 4761. I don't have a calculator and I'm lazy. And so the way I'll do something like this is I'll say, roughly what is it? Well, 3600 is 60 squared and 70 squared is 4900. So it looks like it might be in the 70s. Sorry, it looks like it might be in the high 60s because it didn't get to 4900. So is it in the high 60s? And what squared would end with a 1? 1 squared ends with 1 and 9 squared ends with 1. Those are the only two things that end in 1 when we square. So is 69 squared equal to 4761? Let's find out. That's a random guess. 69 times 69. 9 times 9 is 81. 9 times 6 is 54. This is hard. 62. Okay. By the way, when I did that, I just quickly checked, is that actually a multiple of 9? Because I did 9 times 69, so the answer needs to be a multiple of 9. 6 plus 2 plus 1 is 9. The sum is divisible by 9, so I didn't make a mistake. Now I do 6 times 9 is 54. 6 times 6 is 36. I guess it's 41. Another quick check. Yes, this is also a multiple of 9 because 6 is a multiple of 3 and 69 is a multiple of 3. Let's add them. Oh, it's good. 4, 7, 6, 1. So we got it right. That's 69. Okay. So if you can see, the way that I did this is I was hoping that your answer was nice. And one nice trick you can use is you can just go and say, well, roughly what would it be? If it's a 4-digit perfect square, you can basically guess and say, well, is it like in the 40s, 50s, 60s, 70s, and so on? And then in the squares, here's a neat fact. If you look at the perfect squares, they always have there's 2 ways to get each of the last digits. So for example, well, with the exception of 0, it's like blah, 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 0 squared is equal to blah, 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 0. But if I have blah, 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 1 squared, that's equal to something ending in 1, something ending in 2 squared ends in 4, ending in 3 squared ends in 9, ending in 4 squared ends in a 6, because 4 squared is 16. Oh yeah, and 5 is also special. 5 squared ends in 5. I'm running out of space. But I'm showing you something neat. I know how to do it, because I wanted to show you something neat. So let's go and continue this way, but the other way, which is blah, 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 6 squared. 6 squared is 36. Oh, neat. And if I do something 7 squared, then that's going to be 7 squared is 49. Do you see how it's like going down and then back up? Because if I go with something ending in 8 squared is 64. And if I do something ending in 9 squared, that was supposed to be a squared, then that will be ending in a 1. So it's really that it just kind of went down and then back up. It's very symmetric. And that's really satisfying. It's like somehow if I go one way or go the other way, if I go like increasing after the 5 squared, then I just get to repeat the same thing. By the way, why should that be true? Is there any good reason why that should be true? Well, if I think about it, I'm trying to say what happens to the last digit if I happen to have a number which is like blah, 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 like some multiple of 10. How do I want to say this? No, I have a better way. I can say, I want to say, why is it symmetric around 5, right? It's like 5 is this special thing. And so there's a neat fact. It's like if I have some big number, blah, 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 5, plus something, I don't know how much, let's call it x, and then square it. And what if I compare last digit? I shouldn't have called it x. X looks like a times sign. So let's call it u for units digit. No, that's not right. It's not a units digit anyway. So let's call it like a. A, why not? A is something. Versus blah, 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 5 minus a squared. Do you know what happens if I compare their last digits? This is like some blah, 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 5. So it's like the same number, and that's the same number. But you know what happens when you start to square things? If I have to squaring a number gives me the square of the first thing plus 2 times the product of them plus the second thing squared. Okay? So what I end up getting from this one is I'll get the square of the first thing, which is still blah, 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 5, because 5 squared is 25, ends in a 5, plus what happens with 2 times blah, 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 5 times a plus a squared. Well, something really neat happens here. What happens when I take 2 times blah, 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 5 times anything? Can anyone tell me what the last digit of this is? What's the last digit of this part? 2 times something ending in 5 times any other whole number I want. Well, if I start doing it, the 2 times something ending in 5, magic happens. 0. 2 times something ending in 5 always ends in 0. And then you times it by whatever you want, it still ends in 0. So what you end up getting is you end up getting blah, 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 5 plus blah, 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 0 plus a squared. Now, does anyone know why I did this? Does anyone know why I bothered to do this? It's because if I do it on the other side, you know what's going to happen? If I try to square out blah, 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 5 minus a, whole thing squared, it will look almost the same. But there's only one place that changes. That plus will change to a minus. So if I do the same thing on the other side, all that will happen is that that plus becomes a minus. Well, if that plus becomes a minus, then it becomes a minus here. What happens to the last digit of your number if you just change the plus to a minus on this thing blah, 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 0? Nothing. Like in terms of the last digit, you'll get the same last digit. So I'm going to say that that is why, if I compare them, the other side will be blah, 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 blah 5 minus blah, 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 blah 0 plus the same a squared. So it's the same last digit. So that's actually why it's symmetric. It's like if I go from blah, blah 5 and I go in the same direction on both sides and I square, the last digit is going to be the same. So anyway, that's like neat reason why you have the symmetry going on here. I see. So my quote today is blah, 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 blah. All right. We got about 5 minutes left. What else can we do in these 5 minutes left? Oh, neat. Yen Ying Cho says, did anyone know that every time you get from one square to the next, you always have an odd number? Yes, that's correct. Let me give you a proof by picture. So why is it that when you go from one square to the next, here's a square, that's the area of the square. What's a nice thing for the square? It's like this is a square, okay? To the next. Well, the next is going to be like plus another 1, and plus another 1. Does anyone have a really good reason for why that area here is odd? Well, I have one. Do this. Now what I found out is that there's an area of 1 here. And look, those two are the same area. Same and same. So that means that the difference between the area of the square and the next square is same plus same and then plus a 1. Well, that's going to be odd because same plus same is even. That's like you could line them up and it's going to be an even number plus 1. So it's odd. That's it. Proof by picture, proof by graphic. So that's the reason why the gap between a square and the next square is always going to be odd. Okay. 2 times blah equals odd. Not quite. 2 times blah is equal to even. But then 2 times blah plus 1, that turns it into an odd. Okay. We have 3 more minutes. What else can we do here? I'm trying to find something that might be like answerable in 3 minutes that is here. Oh, neat. Bob Smith has asked, is 0 a natural number? So let's do these kinds of questions. So actually, it depends where you are. I think in some parts of the world, 0 is considered a natural number. In the United States, 0 is not considered a natural number. But that's actually why I don't usually worry too much about those like names for things, because look, if you use a different language, it's probably not even written as natural number. That's English anyway. So the important thing is to just think about the math, like what you've just seen here. And those exact names, it's good to know what they are, but we won't dwell on exactly who is right and who is wrong, because I wouldn't go and say that the French are wrong if they happen to go and use different notion of natural number. Oh, let's finish with this one. Compute 300% of 0.03. Let's finish that one, because this is a quickie. What is 300% of 0.03? So interesting things that you can do here are, okay, I thought I'd have something interesting to say here. But actually, here probably all I would say is 300% that's just 3 times. Because that's a nice thing. 3 times 0.03. So we're done! It's 0.09. Because 300% was nice enough. Okay, anything else that we can do here? Blah divided by blah is undefined. Blah. It's also dangerous. It's also dangerous because you don't know if you divide it by 0. So blah divided by blah is blah question mark. We don't really know if it's defined. Oh, here's a neat one. Annie Tsui. Let me finish with, it's the one right before. I think it's Arun, who asked, is 1 a prime number? That's a good one. So the answer is 1 is not a prime number, but the reason is because prime numbers are really useful, sort of as building blocks for making numbers. You can think of it as every whole number, every natural number, except 1, has a recipe for how it's built. Because as you saw, like the number 25, that's special because that's a 5 and a 5, right? And so when you're trying to build up a number, you think of using the primes to build them up by multiplying them together as different ingredients. It's just like all the odd numbers are somehow quite different than all the even numbers. And that's because the even numbers have a special ingredient called 2 is a factor. So that's why 1 is not considered a prime number. 1's not useful as one of these like building blocks for making numbers. But also 1's not composite either. So 1's like neither prime nor composite. Okay. And the other thing is, like, sometimes people wonder who cares about prime numbers. It's because that's how you can think of how you built up numbers. And so prime numbers are a useful concept for that reason. With that, we actually, unfortunately, have finished the AMA. Today's session was only going to be 45 minutes long, but we'll be back. I think actually, I forgot what's on next week. But the way this works is that whenever there is not a collaboration that we're doing, we try to run an AMA for people to see. Although I will say, actually, next week some interesting stuff is happening, which you will probably hear about in other ways. So I'm actually not sure that we're going to have an AMA next week. We'll update the main website for that. That's the poshenloh.com/live. But with that, I'm going to wish all of you a great rest of the weekend, and good luck with whatever you're doing. Enjoy the weather, hopefully, wherever you are. And I'll see you next time. Bye-bye.